Hello, my name is Fernando Gama, and I am currently a postdoc in the EECS department at UC Berkeley. I received my PhD from the Electrical and Systems Engineering department at Penn last June 2020. Today, I'm going to talk about graph neural networks and collaborative intelligent systems. The reason why I'm going to talk about graph neural networks is because I want to do machine learning on network data. In network data, the signal structure is given by a graph, the underlying network, and we want to leverage it in learning from network data. In particular, I'm interested in processing data of arbitrary dimension, which demands scalability. I am interested in exploiting data structure by using local information in order to train faster, and I am also interested in learning models that admit distributed computations for an efficient implementation. All of these are characteristics of graph neural networks. Graph neural networks, or GNNs, are built from graph convolutions that are local and distributed linear operations that generalize time convolutions. I will prove equivariance and stability properties of GNNs. These are two properties that, together, justify that GNNs transfer and scale. To demonstrate the practical relevance of GNNs, I will show you their application to distributed collaborative intelligent systems. These consist of a team of agents that need to collaborate to accomplish a global task. The autonomy of agents implies distributed actions based on partial information. I will show you that GNNs are the key enablers for solving this tension between a global objective and local actions. GNNs are built on graph convolutions with generalized time convolutions. A time convolution is a linear combination of shifted versions of the signal x. If we want to extend this concept to graphs, we need to have a notion of shift. This notion of shift is defined in graph signal processing to be a matrix description S of the graph. So the traditional notion of shift in time is equivalent to applying the shift S of a graph. When we consider an arbitrary graph, applying the shift amounts to diffusing the signal. So, a graph convolution is a linear combination of shifted versions of the signal. The effect of the shift operator is to update the signal with a linear combination of neighboring values. Thus, this operation is entirely local. A GNN is then defined as a cascade of layers, each of which applies a graph convolution followed by a pointwise nonlinearity. The GNN depends on the filters H, which we learned from training data, but also depends on the graph structure S. A GNN is a non-linear mapping that exploits the underlying structure S, it relies on local information only, and has a distributed implementation. But why GNNs? Why are they good at machine learning on graphs? First of all, I proved that GNNs are permutation equivariant. This means that a reordering of the nodes results in a corresponding reordering of the output of a GNN. This implies that GNNs exploit the graph structure so they scale, learn faster, and generalize. But the graph convolutions by themselves are also permutation equivariant. Why choose GNNs? Well, because GNNs are stable and linear graph filters are not. I proved that GNNs are stable to perturbations, meaning that a small change in the underlying graph causes a small change in the output of the GNN. The stability result gives valuable insight when considering the graph frequency domain, where the frequency response of the filters gets instantiated on the specific eigenvalues of the graph. When the graph changes, for example due to a graph dilation, we see that small eigenvalues change little, but large eigenvalues change a lot. Stability implies that either the eigenvalues do not move much, or the filter does not move much. When we want to discriminate high eigenvalue frequencies, we use narrow filters. The problem is that even a small dilation will cause large eigenvalues to fall outside of the passband, making the filters unstable. Thus, linear filters are either stable or discriminative, but cannot be both. GNNs apply nonlinearities that have a frequency mixing effect akin to the modulation. Now that the frequency content has spread into lower frequencies, we can stably discriminate these signals. Thus, GNNs are both stable and selective information processing architectures, where graph filters are not. Let's consider the problem of learning distributed controllers. A distributed system imposes a distributed and delayed information structure. Thus, distributed controllers can only depend on this information structure. Optimal distributed actions are difficult to find, so we resort to data-driven heuristics. In particular, we adopt a learning architecture that naturally processes distributed information. That is, we adopt a GNN. In fact, permutation equivariance of GNNs will play a key role in scalability, since similar neighborhoods will undergo similar processing, while stability plays a key role in transferability, since if the graphs are similar, the GNN outputs will be similar. In the application of flocking, we want the team to coordinate on their individual velocities without colliding with each other. We want to learn a distributed controller based on neighboring information, so we adopt a GNN. We show the results of training on 50 agents and testing on 50 agents, and we see it works. But we see it also scales and transfers, since we take the same trained architecture on 50 agents and test it on 75 agents and still works, and even 100 agents and still works. Moving forward, my objective is to develop the theory of machine learning for signals with unconventional structure, graphs being one example. I want to do machine learning that scales, so I need to design architectures that exploit this structure. I will operate from first principles to develop theoretical results and performance guarantees, since our intuition is quite limited beyond Euclidean domains. I will also keep exploring GNNs as the enablers of solutions in distributed collaborative intelligent systems.